And I'm going to edit you out of all. Okay, here we go. Sequences is what we talked about last time, right? And all it is just it's just a list of terms that come in order, right? That's all a sequence is. And we've decided that there is a lot of value to sequences that either converge to a value or converge to 0. So, now the question is, what happens when we add up all the terms in those sequences? So, infinitely many terms, okay? And that is what we get. What we get when we do that is called a series. So here we go. We're going to start talking about series. Now, I'm trying to remember, it's been a week and a half. We talked about the difference between an arithmetic and a geometric sequence, but not the arithmetic and geometric series, right? We talked about the arithmetic sequence, the terms have a common difference, right? We add the same thing over and over and over and over and over again, right? And the geometric sequence, geometric, not arithmetic, but geometric, you have a common ratio. You multiply something repeatedly, right, for each term. Okay. So what does that look like when we add them up? So for a series, a geometric series, we would start with some number, and we'll just call it A. Then what we would do is we would multiply that by the common ratio in the second term. And then in the third term, we would multiply that again by the common ratio, and we would wind up with AR squared. And then we would just keep doing that. So we would have AR cubed. Now, the thing that we want to realize is that for each one of these terms, the exponent on R is one less than the position of the term. So in the first term, so here we have the first term, we don't really have an R written here, but we could if I put an exponent of 0 on it, right? And then in the second term, I have an exponent of 1, and on out. So what we have then is that the exponent on R is 1 less than the position of the term. Okay, so then this would be n minus 1, right? If that's the nth term. Okay, now here comes some notation. If I was to add that forever, never stop, then here's what would happen. I could write this as a sum, right? And we're accustomed to using that sigma symbol. But what I'm going to do is I'm going to say, all right, the terms will start with the first term and then never stop. So the nth term starts at the first term, 1, and then goes on to the infinitieth term. The last term would be out at infinity. And each one of these terms in this series would have this form. A times R raised to the n minus 1. Okay, now let's suppose that R is not equal to 1. So let's do this. Let's give this notation S sub n. That's going to stand for the sum of the first n terms. So that notation is going to stand for the sum of the first n terms. Okay, so what would that look like then? Okay, so S sub n would be equal to A plus AR plus AR squared plus AR cubed, just like we have written up there, but I'm rewriting it again for a reason. I don't want to include anything beyond the nth term. So this is a finite sum, a finite number of terms, and that's going to have a finite value, right? If I'm going to stop somewhere, then I'm going to have an actual sum for this thing. So the question is, well, what if that thing goes on forever? Do I have a finite sum? But at first, though, let's see what we could do with this to come up with some sort of a formula for what the sum of the finite sum for a geometric series would be. So let's see if we can come up with a formula for that. So let's do this. Let's multiply both sides by r. Okay, so we'd have RSN equals, okay, now each one of these then has another r. So AR plus AR squared plus AR cubed plus ... plus ARN minus 1 plus ARN, right? Everybody okay with that? Okay. So now let's do this. Let's subtract the top one from the bottom one. Okay, and let's see what happens there. So in other words, I'm gonna take this one where I've multiplied r on both sides, and I'm gonna subtract from that this one right here. And you know, I tell you what, let me take that back. We'll do this in a different way. Rather than you guys having to rewrite your notes, we'll just do it this way. This is totally fine. It doesn't matter how we do it. So I'm just going to subtract the bottom one from the top one. It doesn't matter. Okay, so let's see now. That means that all of the terms in this one here are going to wind up being negative, right? Okay, so what do I wind up with over here? I wind up with S sub n minus R S sub n equal to... Now, here's something I'm noticing. Everything on the right-hand side, except for the first one and the last one, are going to cancel, right? So I'm going to wind up with A plus minus AR to the n, right? So the first one of the S sub n series and the last one of the R S sub n series would just go away. Okay, so let's see. I'm trying to get a formula for S sub n, instead of writing it as A plus AR squared plus AR cubed and all that. I want it just to be S sub n by itself. And I've got it in two terms over here on the left. But that's okay. I can just factor an S sub n out. So I'd have S sub n times 1 minus R equals A minus AR to the n. And, well, let's see. So I could divide both sides by 1 minus R. So what do we wind up with? We wind up with S sub n equals A minus AR to the n over 1 minus R. So there's a formula, then, for a finite geometric sequence. Any questions about that? What we were doing and why we did it and all that kind of stuff. Oh, yes, sir.
When you multiply both sides by r times a to the r n minus 1 plus a to
Well, and see, what I didn't do in the one above was write the plus AR to the n minus 2, right? So you see that the AR to the n minus 2, you got it now? Okay. Okay, any questions, sir? Everybody good? All right. So now, let's see. I could factor an A out of that. Let's do that on the next page. So we'd have S sub n equal to A, and let's go back here now. I'm going to factor an A out of there. So I'm going to have 1 minus R to the n, right? Over, and then 1 minus R, like this. Okay, so I know what you're thinking. You're thinking, I'm not really worried about the finite sum here. I'm worried about the infinite sum, right? How can I get that? I bet you a limit would do it, right? We want n to go to infinity, right? So what if I did that then? What if I did the limit as n goes to infinity of S sub n? Okay, so I'm doing a limit on both sides, right? Limit as n goes to infinity, A times 1 minus R to the n over 1 minus R. I don't know. I mean, n's going to infinity, but what in the world does it do to that thing? Well, I tell you what. Let's do this. Let's look at a case. Okay, so let's let the absolute value of R be less than 1. So in other words, if we look at a number line, R is somewhere in that region right there, right? Between -1 and 1. Okay, so let's think about that then. Here's what I'm thinking. I am thinking that that A is constant, isn't it? I'm thinking that can come out in front of the limit. Okay. So I'd have A limit n goes to infinity 1 minus R to the n over 1 minus R. Okay, so now I'm thinking, well, I could actually make that 2 limits, couldn't I? Okay, so this could become A limit 1 over 1 minus R minus A limit R to the n over 1 minus R. Okay, now, what do you notice about the first term? What's variable in the limit? Oh, n goes to infinity.
If R is a constant, then it approaches a constant value in the first term.
Well, yeah, so basically what happens is if we don't have an n in that first term, 1 over 1 minus R. So everything in there is a constant relative to the limit, right? So that first term is just, well, it's just A over 1 minus R, isn't it? Okay, I can write that. Now, the second term. What can I do with the second term? Well, the denominator is constant, isn't it? Okay. So that means that I could write this thing as A over 1 minus R times the limit as n goes to infinity of R to the n, couldn't I? Now, let's think about this. So R is less than 1, right? So what happens to the limit as n goes to infinity for things that are less than 1. Yeah, when I put I meant to put the exponent up there. When I raise it to the nth power, it gets smaller and smaller and smaller forever until it goes to 0. Okay, so how cool is this? So what this means then is that if we want to find the sum of an infinite series, an infinite geometric series, when r is between -1 and 1, then we can use that formula. So here we go. Let's write that down. Let's say if the absolute value of r is less than 1, then the sum n equals 1 to infinity a r raised to the n minus 1. Important detail there. Will be just what we have here. A over 1 minus r, right? Now, what this means is that if the common ratio is less than 1, if the absolute value of the common ratio is less than 1, then the series would be convergent. Very good. And that is the big detail, right? That's the thing that we're after, is whether or not things converge or diverge. Okay, now, here is the rest of that. If we are outside of -1 and 1, if r is outside of -1 and 1, then the geometric series is divergent. Okay, so it's going to be real important that we're able to identify when something is geometric. It may not look geometric, but maybe we can manipulate it so that it does, so that we can see that it is geometric. Okay, let's look at the arithmetic series real quick. So, if we have a finite arithmetic series, so here's what an arithmetic series would look like, a finite arithmetic series. Now remember, with an arithmetic series, we add a common difference over and over and over. Okay, now that is finite, right? It stops. I didn't let it go on forever. And this formula, and I don't know if you guys have ever heard this story about Gauss. You ever heard the story about Gauss where he adds the numbers from 1 to 100 and comes up with a formula to do that? It's very cool. It gives you a kind of a vision into how brilliant Gauss was. He's considered to be one of the 3 most brilliant mathematicians of all time. But he, apparently, this is the story when he was a kid, his teacher, the teacher wanted the kids in the class to add up all the numbers from 1 to 100 to keep them busy, I guess. And it only took him less than a minute. And the teacher said, "Okay, how'd you do this?" And he says, "Well, I wrote them down in this direction." Of course, he said all this in German. And then I wrote them all down in this direction. And I realized that they all add to 101. And there were 100 of them. Okay, so here I've got 100 101s, which that sum would be 100 times 101. But that's too big. It's twice what I wanted because I've added 100 from 1 to 100 twice. So I'll just divide it by 2, and I'll get that sum. the formula that came out of this is then that if you are going to add all of the numbers, from 1 to some value, you're just going to do this, 1 to whatever n is, times n plus 1 divided by 2. So that would be the sum for an arithmetic series. But now here's the thing, a finite arithmetic series. But here's the thing. That limit, if we think about the limit as n goes to infinity of n times n plus 1 over 2, is there any question what that is? No, we can't manipulate that in any way and make it be anything other than infinity, right? So infinite arithmetic series are divergent. That's always the case. Infinite arithmetic series are divergent. And we need to be able to recognize that too, because something being divergent is just as significant as something being convergent. Okay, so here, let's do this. Now, what I'm doing here is, in this next example, is we're leaving the geometric and arithmetic. We're looking at all different kinds of series here. So we looked at geometric, we looked at arithmetic. Now we're going to look at, it really does get fun if you just sit and do it. Just sit and do it, and it'll get fun. It'd be like, doing little puzzles and stuff. Way better than Sudoku. Okay, so let's suppose that we have this series. Sum n equals 1 to infinity. Now, I'm going to infinity here, right? This is not finite. This will be an infinite series. And it'll look like this. 1 over 2n plus 3 minus 1 over 2n plus 1. Now, I'm looking at this and I'm going, well, if I wanted to combine those two, I'd have to get a common denominator. That'd put an n in the top. And so now I'd have something infinite in the top and something infinite in the bottom. So what do I have? I don't really know. But maybe I could look at the terms. So this is going to be a technique that you are going to sock away as something that I might try sometimes. Okay, so let's list the terms. So let's start with the first position. So in other words, if n is equal to 1, and then if n is equal to 2, n equal to 3, and on out, and just see if we can see something happening. Okay, so the first one. The first term, if n is 1, okay, so I'd have 1/5 minus 1/3, wouldn't I? Okay, that's the first one. Now, it's a series, so I'm adding them up. So the second one, that'd be 1/7 minus 1/5, right? And then the third one, I'd have 1/9 minus 1/7. Now I'm starting to see a bit of a pattern here. That 1/5 in the first term here, where's the little, there he is. That 1/5 is positive, and that 1/5 is negative, so they're going to cancel. That 1/7 is positive, and that 1/7 is negative, so they're going to cancel. So it looks to me like I might be able to come up with a reliable representation of this pattern here. So that wouldn't contain nearly as many terms. Okay, so now let's do this. Let's look at the n minus 1th. Oops. So the n minus 1th term and then the nth term. Let's look at those and see what we can come up with here. So n minus 1. So if I put n minus 1 in for n, so I'd have 1 over 2n minus 2 plus 3. That's going to be 1 over 2n plus 1, isn't it? And then if I put n minus 1 in the n for n in the second term, so I've got 2n minus 2 plus 1, so that's going to be 2n minus 1, right? And I'm going to need to move that one to have space. So the nth term here. So now I'm going to, well, if I put n in there, that's what I've got, right? I've already got it up there. So I'd have 1 over 2n plus 3 minus 1 over 2n plus 1. Now, I'm not really through here because, I mean, I'm going on forever, right? Except for the fact that, well, I've got it represented in terms of n, right? So in my summation notation, I've got n goes from 1 to infinity. So n could be infinity and this couldn't it? I'm looking at the nth term. I'm going all the way out to the nth term. Well, what happens? Well, okay, just like we talked about a second ago, the outer terms are going to cancel, aren't they? So actually, that one is eventually going to cancel with 1 out here, right? So the outer ones are going to cancel. And I can actually see that outer one and that outer one are going to cancel. And this outer one was going to cancel with 1 back here, right? Okay, so it's only the inner ones that would remain. And as a matter of fact, only the first inner and the last inner would remain, right? So how does this thing end up then? So this thing just ends up as being minus 1/3 plus 1 over 2n plus 3. Okay, so let's see. What about this limit? The limit as n goes to infinity of minus 1/3 plus 1 over 2n plus 3. Well, that limit is just going to be minus 1/3, isn't it? So here's what you take from this. First of all, it's convergent. But here's the thing. Is this kind of crazy? If you add that up for infinity, forever, and never stop, you're only going to get minus 1/3. And you'll get minus 1/3. You'll get a number. It will be a number. It won't be, a theoretical thing. It's a fixed thing. Okay? Any questions about any of that? So that's a technique you might look for. But I know what you're thinking. You're thinking, we have done all this work in the past few weeks. I don't want this work to, go to waste. I want to use it again. So what if I have something like this? What occurs to you when you see something like that?
Exponents at the bottom.
Yeah. What else? With regard to something we've done in the past.
Difference of squares in the bottom.
You could factor it. Okay, but let's see about that. Still didn't help me though, did it? I want to find out what that sum is. What does it look like something we've done in the past? It looks like partial fraction decomposition, doesn't it? Like something we could turn into two terms and then maybe we could figure out what the sum is. Okay, well, let's do that. Okay, so we're going to go like this. 2 over 2n plus 1, 2n minus 1. We could write as a over 2n plus 1 plus b over 2n minus 1. Yes?
Where did you get the 2 in the numerator? Should it say 4?
Yes, and you see, when I misspell things, I expect the iPad to correct me, and it didn't do it that time. I don't know where I got the 2.
You said you were too considerate with the rest of the problem.
Yeah, very good, very good. That was really good. You need a drink and a cigarette. Okay, so let's multiply both sides by 2n plus 1, 2n minus 1. Okay, so what do we got now? We have 4 equals, now the 2n plus 1 is going to cancel in the first term. So we have 2a, I'll tell you what, let me do it this way. What's going to be, I think what I'm going to do, yeah, no, I'm not going to do that. I'm going to go ahead and just write it like this. A times 2n minus 1 plus b times 2n plus 1. There. That's making sense, right? Okay, then we can multiply all this out. So we have 4 equals 2an minus 1 plus minus a, yes, very good, plus 2bn plus b. Now, how many n's do I have on the left?
2.
Yeah, I don't have any, do I? So here's what I know. I know that 2a plus 2b is going to have to be equal to 0, isn't it, in order for these two sides to equal each other. And then I also know that minus a plus b is going to have to equal 4, right? Okay, we could multiply the second equation by 2 and make those a's go away nicely, couldn't we? So we'd have, we'd still have 2a plus 2b equals 0. Now we're multiplying the second one by 2, so we have minus 2a plus 2b equals 8. And when we add these together, we get 4b equals 8, and so b is equal to 2. Now, if minus a plus b is equal to 4 and b is 2, then I think that a is going to have to be negative 2, isn't it? And then we could check that in our top one too, which would also give us minus 4 plus 4 is 0. Good. All right, so what does this mean? This means that I can rewrite this thing, this whole thing here, as, so let's see, what are we going to have? We're going to have sum n equals 1 to infinity, minus 2 over 2n plus 1, plus 2 over 2n minus 1. And that's exactly the same, right? Okay, so now take a second and do what we did in the last problem and see what you come up with. So did you find... my notation actually could have been better here, by the way. Just to be clear, what I'm doing here is I'm using an I and an N here, which I should have done in the last problem too, because I'm saying, okay, my position goes from 1 up to n because we're finding a finite sum here, right? I'm going to the nth term. And so, and then we'll find a limit as n goes to infinity. Does that make sense? My notation could have been better earlier. Okay, so here we go. What we find is that it's the same this time. It's the inners, right? Now, it's not always going to be like that. Sometimes it might be the outers if you're going to use this technique and it's going to work. But what we wind up with is a 2, and then we wind up with minus 2 over 2n plus 1. Okay, now, if I want to find the limit as n goes to infinity of 2 minus 2 over 2n plus 1, well, that's 2. So again, I've got this thing, sum n equals 1 to infinity of 4 over 4n squared minus 1. And if I add infinitely many terms up that look like that, the result is going to be 2. Any questions about any of that? Is this expanding your mind? Yes, sir.
So it's only 2 when n reaches infinity. It's not 2 on any point in the summation.
That's right, because you would have terms that haven't yet canceled out. Yeah. Okay. How about this? How about the sum? Now, look here. I'm doing n equals 1 to infinity, so this is going to be an infinite series. 3 times minus 1/2 raised to the n minus 1. What do you think? Anybody have an idea?
Use the formula at some point, right?
Well, why? What is it?
It's geometric.
Yes, it's geometric, right? We need to be able to recognize when things are geometric. Okay, what was that again? So geometric series look like this. 1 to infinity, AR raised to the n minus 1. So we can identify here real clearly what's what, right? So we can see that A equals 3, R equals minus 1/2. And the important thing here is that R is between -1 and 1. That's the important thing. So we know then that this is going to be a finite value. This is a convergent geometric series. Okay, so how do I find the sum? Now, by the way, you remember back here, I put an n in the subscript here for the finite sum. I put an n there. Well, when we look at the infinite sum, for a geometric, sorry. The infinite sum, so this right here, you don't put an n in the subscript, you just say s. So just so you understand, when you see that notation in your textbook or on your problems, when you only just see an s, it means the infinite sum, not the finite sum, okay? And that formula was A over 1 minus R. Okay, so for this one then, we're going to have 3 over 1 minus -1/2. So we have 3 over 1 plus 1/2, so 3/2, which we would then just invert and multiply, and we're going to get 2. But I mean, seriously, you could have done that in the 4th grade, right? But what you couldn't have done in the 4th grade was this. What about this guy right here? E to the n over 3 raised to the n plus 1. Oh. What do you suspect? What do you suspect?
My first instinct is to get them to have like exponents.
Okay. So are you thinking, well, when do you add exponents? In what condition do you add exponents?
When you multiply, but in this case you divide.
When you multiply with like bases, right? Okay, very good. So in other words then, what you are saying to me, Everett, did you get named that because it rolls off really nicely when you're pissed? Everett, like that?
Nobody calls me that.
Missing an opportunity. Okay.
Nobody gets angry at me.
I don't believe that.
All right.
Can we have a show of hands? All right, so here we go. Here we go. So what you have suggested is that we write this, right? Okay, I think we're making progress here. But here's the thing. I'm thinking it looks almost geometric, but not quite. What is it about the geometric form that we don't have here? And minus 1. Okay. But I tell you what we could do, though, to maybe get started going there. We could maybe do this. We could go 1/3 times e over 3 to the n, couldn't we? Because that's when we have a quotient with the same exponent like that, we can make it, that power of that quotient. And we could do, again, what we did a second ago with a 3, right? Like I could write this as sum n equals 1 to infinity 1/3 times e over 3 times e over 3 raised to the n minus 1. So let's see, cleaning that up a little bit. So we have sum n equals 1 to infinity e over 9 times e over 3 raised to the n minus 1. Now, am I in a geometric form? I am. Okay, so let's identify what A and R are. A is going to be e9ths, and R is going to be e3rds. Now, what's significant about e3rds? How big is E?
It's less than 3.
Less than 3. And since it's less than 3, e3rds is less than 1. Sweet. Okay, so here's what we know. We know then that this is a convergent geometric series. And its sum, A over 1 minus R, would be e9ths over 1 minus e3rds. Okay, well, let's see. We would need to get a common denominator here, or multiply top and bottom by 9. We could do that. Complex fraction. That's what we mostly would do anyways, right? Multiply top and bottom by the lowest common denominator. So we would wind up with e over 9 minus 3e. Not sure I can write it any better than that. I'm just going to leave it like that.
Pearson has deemed your answer incorrect.
Probably.
2 million decimal places in, it's off.
Say that again now.
2 million decimal places in.
Oh, okay. Yeah, we had to figure that out, didn't we, Josh? Okay. I had thought that Josh had like just made some like huge mathematical discovery on his first test. Okay, so here we go.
But he didn't, so let's. Sorry.
All right. So, harmonic. The harmonic series.
Now we're going to the music theory.
That's my jam.
It almost seems like the harmonic series should be called the dissonant series because it diverges. You would think the harmonic series would converge, right? But this guy actually diverges. So it is important that it's another series we need to be able to identify because what we're headed towards is deciding when series are convergent and divergent, even more so than what they converge or diverge to. And we know this one is divergent. And let's think about this for a second. If I know that the terms of another series are all bigger than this one, then what would have to be the case of that series? It'd have to be divergent too, wouldn't it? Because the sum would be even bigger. Okay, and that that's a theorem. But however, anything we do, we can't just say that. Like, oh, the terms are bigger, therefore. No, things have to be proven, right? So, but that is a thing that we will do. We will use series that we know about to prove things about other series. Okay. So here's what I would like for you guys to do. Do I want to do this one right now? Yes, I do. Yeah, I do. Okay. I would like for you, please, to come up with whether or not this thing converges, and if it does, what does it converge to? So just goof around. This is something you're gonna do a lot. Just goof around with your pencil and paper. So is this what you guys did? Did you make it two fractions and then call one of them 3/5 times 3/5 to the n minus 1, and then the other one 4/5 times 4/5 raised to the n minus 1? And then the nice thing about that is that we have convergent geometric series, two of them, right? So the first one would converge to, okay, so what's the formula again? A over 1 minus r. Okay, so the first one is going to be 3/5 over 1 minus 3/5. And the second one will be 4/5 over 1 minus 4/5. So we have 3/5 over 2/5 plus 4/5 over 1/5. And then we'll multiply top and bottom by 5. So we wind up with 3/2 plus 4/1. And so we wind up with, 11 halves? Any questions about that? All right. How about this one? How about sum n equals 1 to infinity, 2 to the n over pi raised to the n plus 1. So did you do this? Did you call it 2 over pi squared times 2 over pi raised to the n minus 1? And then, so let's see, a is 2 over pi squared. 1 minus r is 2 over pi. So we'll multiply top and bottom by pi square. And we wind up with 2 over pi square minus 2 pi. Sorry. And I don't think we can make it any nicer than that, unless Pearson argues. Okay? Any questions? All right. Try this one. Sum n equals 1 to infinity, 2 raised to the 2n, 3 raised to the 1 minus n. So did you wind up with 4 times 4/3 to the n minus 1 in your effort to make it geometric, which it is, right? And what do you know about that?
A is 4. Sorry, go ahead.
Yeah. A is 4, R is 4/3, and so what?
It's divergent.
Yeah, it's divergent, right? Yeah, very good. Now, here's what's going to happen. So, remember how I talked about your problems are going to be arguments that are complete arguments. So we have a complete argument here. I mean, it's all written in mathematical language, but there's no leaps anywhere. We've not done anything that, that required a theorem that we skipped or anything like that. No hand waving at all. But the answer is going to be a conclusion to the argument, and that would then be that, therefore, the series is divergent. Okay, any questions? Okay, so here we go. Theorem. If the series sum n equals 1 to infinity, a sub n is convergent, then the limit as n goes to infinity of a sub n is equal to 0. Now, so let's see, what is that bottom part saying? The limit as n goes to infinity of a sub n, that's 0. A sub n is the terms of that series, right? So in other words, it's the same as the sequence, right? The terms of the sequence. Now remember how when we were talking about sequences, I kept making a big deal about whether or not the sequence converges, and if it converges, does it converge to 0? Is the last term 0? Well, this is what I know. If the series is convergent, then the last term is 0. So if the last term is not 0, then what? The series has to diverge. So this is one of the things when I'm going through those arguments. This might be something I might check. If I have a suspicion that a series is divergent, I might just check to see about that last term. If I can figure out something about that last term. If it's 0, well then I guess I need to figure something else. I need to figure out something else. But if it's not 0, I can stop because the thing is divergent. Is that making sense? Now here's what you got to know, and you got to keep in mind, and don't fall into the trap. There's a hole waiting for you to step in it. And that is that the converse is not true, generally. So the converse is not generally true. I mean, it could be true for some, but not true for all. So you can't depend on it as a test for convergence, the converse of this, which would be if the last term is 0, the series is convergent. That's not generally true. Okay? So, in other words, if the limit as n goes to infinity of a sub n is 0, it does not imply that the sum n equals 1 to infinity of a sub n converges. So we can't depend on that as a test for convergence. What we can do is use this theorem as a test for divergence. Okay? All right. There we go. Now, so what I just said was a test for divergence. And what we're about to do is look at a bunch of tests. Tests for convergence. Okay, so let's see. First one, the integral test. Suppose f is a continuous positive, and I'm going to come back and hit this positive and decreasing thing here in a second. So is a continuous positive decreasing function on the interval 1 to infinity. And let a sub n be equal to some function I can define where the domain would be the position of the terms in the sequence. Okay? Then the series sum n equals 1 to infinity a sub n is convergent if and only if the improper integral, okay, now I see why we did that. The improper integral 1 to infinity of f of x is convergent. So, in other words, let's write this down in some cases here. What does that if and only if thing mean? So, in other words, if the integral 1 to infinity f of x dx is convergent, then the sum n equals 1 to infinity of a sub n is convergent. So if the integral is convergent, then the sum is convergent. So that's the integral test. Okay, but what's the second part of that? This is where the if and only if part comes in. If the integral from 1 to infinity of f of x is divergent, then the sum n equals 1 to infinity of a sub n is divergent. Now, I'm going to come back and talk about this decreasing part here. So, it says decreasing on the interval 1 to infinity. But suppose we have some sort of a function that looks like this. So it increases to there, but then starts to decrease forever after that. Now, what about, well, let's do it back here. So it increases to there, okay? So something that we might call, L, let's say. Then it decreases beyond that. Well, what about the area under the curve from 1 to L? That's finite, isn't it? The question is, what about the area from here on out? Is that finite? Now, if I add two finite things together, I get a finite value, right? And so if the integral is convergent, so in other words, if that improper integral gets me a finite value, then it's convergent, right? We've done this. Okay, and so I don't really have to be decreasing everywhere, because up to any point, I have a finite value finite area underneath that curve. The question is beyond that point. So it says decreasing on the interval 1 to infinity. Well, it doesn't have to be from 1. It can be from anywhere. Okay, you guys get the idea there. Okay. So, let's look at, and we have already looked at this to a degree before, and so we've kind of started this argument somewhat. So the sum n equals 1 to infinity 1 over n squared plus 1. That's a sum of squares, right? Well, that's probably not something I'm going to do like a partial fraction decomposition on, because it's already partial fraction decomposed, right? Okay, so, well, what can I do? Well, first of all, we might note that this function is continuous. Now, remember how I said that our arguments have to be complete. Okay, so this thing is continuous. We could graph it. I mean, if we look at it forever, it's going to peak actually when n is 0, right? That'll actually be a value of 1, won't it? It'll peak at 1. But for any other, the value of n, I mean, I'm going to take, in the denominator, I'm going to go 1 plus something. Now, the farther out to infinity or negative infinity we get, the bigger the denominator gets, the smaller the fraction gets, right? So we have an asymptote on the x-axis. The other thing, though, is that between 0 and 1, the n square values actually, when you square something between 0 and 1, it gets bigger, doesn't it? Yeah. So it's going to have a behavior that's going to look like this. And then that x-axis is going to be an asymptote. Okay, so the thing is continuous. Well, it's also positive, isn't it? And we've also decided that it is decreasing on 1 to infinity. Okay, so let's go back and look at the integral test. So it says if I have a function that is positive, is continuous, positive, and decreasing on the interval 1 to infinity, and I can define the terms of a sequence in terms of that function, then the series is convergent if the improper integral is convergent. So it looks to me like if I want to find something out about that series, I could look at the integral. Okay, so let's do that. So I'll have the integral from 1 to infinity of 1 over x squared plus 1 dx. Now, from what I know about improper integrals is I have to make a limit out of it, right? So I have to say, okay, well, this is going to be the limit as t goes to infinity, 1 to t, 1 over x squared plus 1 dx. Well, I think I know something about that. That's going to be the limit as t goes to infinity of what? Yeah, very good. Evaluated from 1 to t. Okay, so let's see. I always like to look at the graph of the tangent function whenever I'm working with this inverse tangent function. So let's see what that looks like. I know that this thing has asymptotes at minus pi over 2 and pi over 2. So if you're not real strong in your trig, hopefully you're working through that. But this is a way you can always figure out these arctangent values if you're struggling with that at all. So I just graph the tangent function. Then I say, okay, the inverse tangent function, this value here is a ratio, right? And what I get back is an angle, right? When you do the arctangent function, what you get back is an angle. So that's what you're looking for, is that angle. Okay, so let's see. So let's go ahead and write this out. So the limit as t goes to infinity, this is going to be the inverse tangent of t minus the inverse tangent of 1. Okay, so let's see. Well, let's think about that inverse tangent of 1 to start out with. Okay, so there's the tangent function. Remember that 1 is a ratio, right? That's a ratio. I need the angle that gives me a tangent function of value of 1. So there's the tangent value of 1. What is the angle that does that? And if I drew this more better, it would come down right about there. And what would it be? Pi over 4. Yeah, good. Okay. All right. So really what I have here is the limit as t goes to infinity, inverse tangent of t minus pi over 4. Okay, so now let's see. T goes to infinity. Okay, now t is a ratio. So that's the function values themselves, these that are going off to infinity up here. And what's the angle going to as t goes to infinity? Pi over 2. So this whole thing then winds up being pi over 2 minus pi over 4, which is pi over 4. Now, so is the integral convergent? Yes, it is. What does that tell you about the series? That it is also convergent. Very good. But we need to write this well, right? Now, so far, I mean, we got a pretty good looking argument going here, don't we? It's got graphs and all kinds of stuff. Let's look at it all the way through. Make sure that we don't have holes in our argument. Again, these are arguments. Okay, so I've indicated that the thing is continuous, positive, and decreasing on the interval 1 to infinity. So then I said, all right, I'm going to use the integral test, and I'm going to evaluate the improper integral, which we have properly done. And so we've evaluated it. Turned out that it was pi over 4, so the improper integral is convergent. So now I'm going to finish out my argument. What do I have to do to finish out my argument? Well, really all I have to do is just cite the integral test. So I can say, therefore, by the integral test, the sum, n equals 1 to infinity, 1 over n squared plus 1, is convergent. What's it convergent to?
Do we not know unless we did it?
Yeah, I was hoping somebody would say pi over 4. But yeah, that's right. You can't tell. You don't know. So the integral test doesn't say anything about what it converges to, right? So just because the integral converges to pi over 4 doesn't mean that the series converges to pi over 4. So you can't determine the value of the series from the value of the integral. Yes, sir.
So we've determined that area under the curve represented by the series of 1 over n squared plus 1 is convergent to pi over 4. Because of that, the series itself is also convergent. Because if its area under its curve is convergent, then the curve itself has to be convergent.
Well, okay, so let's say that in another way. Okay?
So
What we found out is that the area under this curve from 1 to infinity is finite. So we figured that out. And from the integral test, if that area is finite, then we know that if we add up infinitely many terms that are in the same form as the function, that it can't blow up. It can't go off to infinity. That's basically what it's saying. Is that okay?
yeah.
Okay. All right. Any more questions? All right. Do you remember we talked about the p-series? I think we did, didn't we? Talk about the p-series?
I don't remember.
We didn't talk about that.
That rings a bell.
Yeah, the form
I
was familiar, but not the
Yeah, I don't know if the name got mentioned, but I do remember it before.
We're talking about it now. Okay. So this is called a p-series. Anything in this form, we would call a p-series. Now this, you're going to use a lot. You use p-series a lot. So the question is, for what values of p is the p-series convergent? So the p-series converges for values of p greater than 1. The p-series diverges for values of p less than or equal to 1. Okay. Henry. Gonna have to get your mom to wake you up a little bit earlier. Your alarm known as mom. Okay, so here we go. So what about this? N equals 1 to infinity, 1 over n cubed. I'm just happy to see you. My day wouldn't have been good if I hadn't seen you, Henry, so I'm glad you showed up. So what about this? So that looks like that P series, doesn't it? And I'm looking at it and I'm going, well, P is 3, which is bigger than 1. So therefore, I think that this thing must converge. Now, because of everything that we know about the P series, that would be enough of an argument to state whether or not this series converges, because we would just cite the P series. So we would say converges, or we could say convergent P series with P equal to 3, which is greater than 1. I mean, that would be enough. What about this one? One over n raised to the 1/3. Well, I would say that that's a P series too, but P is less than 1 here. So I would say this is a divergent P series with P equal to 1/3, which is less than 1. Let's see. Let's look at something here. This sum is equal to pi square over 6. But this integral 1 to infinity of 1 over x squared dx is equal to 1. Now, this is kind of what we talked about a second ago, right? So while we're going through this whole process of doing tests, all these different tests that we do, the integral test, the P-series test, all that stuff, you have to keep in mind that what we are doing, the conclusions that we're going to come up with, have to do with convergence and divergence, not necessarily the value of the series itself. Okay, so because these two things are different, we can clearly see that you cannot infer the value of the series from the value of the integral. Okay. Okay, let's do this. Let's look at a technique that you're going to use. So what we're going to do is we're going to determine whether the sum n equals 1 to infinity of the natural log of n over n converges or diverges. Okay, let's see. Now, is the log function continuous? Yeah, it is, isn't it? As a matter of fact, you know, as long as n is bigger than 0, right? Then that thing is continuous, and all I care about is whether or not it's continuous bigger than 1, right? So the natural log of n over n is continuous, right? Okay, so this thing, so natural log f, so I could define a function f of x equal to natural log of x over x that is continuous. What about from 1 to infinity? Is it positive? Yeah, it is. What about decreasing? How do you know?
N should be bigger.
Yeah, N will be bigger than L and N.
At least like past some point.
Oh.
Has some,
Yeah, because eventually,
because the definition of the natural log of N.
Are we waving hands a little bit?
A little bit, yeah.
I think we can't do that.
Well, it's
I
okay.
think we're going to have to show that it's decreasing. How would I show that it's decreasing? That'd be a great way to do it. Why would that be a great way to do it?
It's the way to change.
so you find when it's like positive or negative.
Exactly. If the first derivative of this thing is negative, then what do you know about the function itself? Yeah, that's the best way to determine if something's decreasing, isn't it? Okay, so let's find that out. So, f prime of x. Okay, well, I've got a quotient rule, don't I? Okay, so I've got x times 1 over x minus natural log x over x squared. Let's see. Well, that's 1 minus natural log x over x squared. Okay, so let's see. When would this thing be negative? Well, it'll be when the top's negative, isn't it?
Any value greater than,
Yeah, so in other words, the only way that fraction can be negative is if 1 minus the natural log of x is negative, right? Okay, now, something that we might note is that the natural log of e is 1, yeah. Okay, and for any value greater than e, one minus the natural log of x would be negative, right? Or one thing here's how I might say that. I might say it like this. The natural log of x is greater than 1, right? For any x value greater than e. Okay, but now I'm looking at terms of a sequence, right? Or terms of a series. So what is n? What kind of numbers is n? Is n e? No, n represents a position, doesn't it? So what am I going to say?
well, E is less than 3.
Okay.
So any value greater than 3,
Exactly. Very good. So I can say, again, it's all about the argument. It's all about the concise and complete argument that is well stated. So, for any n greater than or equal to 3, sum n equal to 3 to infinity. I probably should say it. I should probably say it this way. I should say that from 3 to infinity, natural log of n over n is decreasing, right? I could say that. And I don't really need the rest of it because the rest of it is finite, right? Okay. So now, what does that mean? I mean, I haven't done anything yet, really, have I?
we proved that we can use negative rotation.
Yes, good job, good job. Okay, so here's what we can say. We can say, therefore, we can use the integral test. Okay, so let's do that. So, the integral from 1 to infinity of the natural log of x over x dx. Okay, so now that's an improper integral, so I'm going to say the limit as t goes to infinity of the integral of 1 to t of natural log over x dx. What am I going to do?
I see a function in this term.
I think so, huh? So we can say let u be the natural log of x, then du would be 1 over x dx, right? So I could say then the integral of, well, it's really just u du, isn't it? Which is going to be u squared over 2. So I have the limit as t goes to infinity, integral 1 to t, natural log x squared over 2. Okay, that doesn't look very promising to me. So what do I have? I'm sorry. Don't pay attention to the man behind the curtain. 1 to t. So let's see. What do we have? So we're going to have the limit as t goes to infinity. So this is going to be the natural log of t squared over 2 minus the natural log of 1 squared over 2. That's 0, isn't it? Because the natural log of 1 is 0. What's that going to be? Yeah, that's infinite, man. There is no way to make that be anything other than infinity. Okay, so what's our argument? What's the completion of our argument? So we've shown that this integral is divergent, right? So we can say, therefore, by the integral test, the sum n equals 1 to infinity, natural log n over n diverges. Any questions there? We have a complete argument. It's there's no holes in any of our logic anywhere. We've carried out all the steps that are required. That is what's going to make it valid. Okay, good.